So this one is assignment from Astrophysics and Cosmology topic. The question is, certified variable stars can be used as a standard candles. What is meant by standard candle? So astronomical objects which are having a known luminosity are known as, or stellar objects which are having known luminosity, we know its luminosity, or we can say we know its power. So stellar objects with known luminosity are known as the standard candles. The graph shows how the luminosity L of one type of a specified variable star depends on the time period variation. So the ratio is there like its luminosity compared to luminosity of sun, like ratio. L by L sun here, it means like it's about 2 times or 2.2 times more than the sun, and it is increasing as the duration time period. Specified variable star is identified in the Andromeda galaxy with a period of 3 days. Use a graph to show the luminosity of this star. So we have to show the luminosity of this star is about 2 exponent 29 watts. The luminosity of a sun is given, which is 385, 3.85, 3.85 in 10 power 6 watts, like, or the power of a sun is given. So when we compare this, as I mentioned, the specified variable identified with a period of 3 days. So this is one, like this one is 2, this one is 3, 4, 5, 6, 7, 8, 9, and 10. So first we work out what is the ratio between luminosity of that star compared to that of sun, the ratio. So each line is representing 0.1, so 2.1, 2. Each line is representing, because 5 lines, so 2.5, 6, 7, and 8. So this is 2.8, means the ratio between the luminosity of a specified variable and the luminosity of a sun in the period of a 3 days, it's equal to 2.8. If we need the luminosity of the specified variable, so it will be 2.8 times the luminosity of the sun. And luminosity of a sun is given to us, so it will be 2.8 times 3.85 into 10 to the power 26. So we just multiply them, we'll get the luminosity of this specified variable, which is 2.43 into 10 to the power 29 watts. The unit of the power is watt. Then the radiation flux from a specified variable is measured to be 3.6. So we go the formula which relate the flux, we have to calculate a distance to this galaxy, Andromeda galaxy. So we have the formula luminosity is equals to flux divided by 4 pi d square. Like if there is a star, we know its luminosity, how much radiation we receive from that, that is radiation entering on unit area, that is a flux F. So D is a distance. Or flux is equals to luminosity, because the relation, it follow inverse square law. So flux is inversely, if a distance double, the flux will be half. If a distance, flux will decrease by 4. If a distance is 3 times, flux will decrease by 9. So flux is equals to luminosity divided by 4 pi d square. So we want to work out the distance here, d. The flux is there, 3.36 into 10 to the power minus 17. The luminosity, that is the power of this, which we work out in the previous one, 2.43 into 10 to the power 29. 4, the pi is 3.14 into d square. So we just cross multiply. D square is equals to 2.43 into 10 to the power 23. Then this divided by 4 into 3.14 into 3.36 into 10 to the power minus 17. And because d square, so we take a root. This will give us the distance. That is 2.4 into 10 to the power 22. So distance between this defined variable and us is 2.4 into 10 to the power 22 meters. So using the flux and the power, luminosity, we can work out the distance between uh, the star and the Earth. The standard candle can only be used to determine the distances to relatively close galaxies. Outline the method used by the astronomers to determine distance to more distant galaxies in our universe. Like for a close galaxies, like galaxies which are close to us, we observe their stars, and we can determine the distance by using a standard candle, like considering the flux. We know their flux. But for galaxies which are far from us, how we use a Doppler effect. Like what we work out the Doppler shift, which is a change in wavelength over original wavelength. And after working out in using then after working out a we observe the galaxy, we find like what are the composition of the galaxy, and we compare the wavelength which we receive from the galaxy and the wavelength which we have the same element on Earth, and using that we work out the change in the wavelength. It might be increase or decrease. Divided by original wavelength, we work out Doppler shift. Using a Doppler shift, we work out the speed at which that galaxy is moving. And after working out the speed, we have the Hubble constant, that is because which shows that like the speed at which the galaxy move is proportional to distance, or v is equals to h naught d, or v divided by d is equals to h naught. So if we work out the speed of the galaxy, so v divided by h naught will be equal to d. So if we know the speed of galaxy and we have the uncertainty, Hubble constant is there, but we can work out. So we will know an approximate distance between us and the distant galaxy. So first we compare the wavelength which we receive from the galaxy to a wavelength which we receive on Earth. Then using a change in wavelength over original wavelength, we work out Doppler shift. From Doppler shift, we find what is the speed of the galaxy. From speed of the galaxy, we work out using a Hubble constant or Hubble law, we work out that the distance between us and the galaxy. In question 8, we have Sirius is a binary star system, 8.1 exponent 16 meter from the Earth, and it's a main sequence star. And its brightness, the brightest star in the night sky. Then we have a Sirius B is a white dwarf. What is meant by the term main sequence star? The star that undergo a fusion, hydrogen fusion, and the radiation pressure is equals to the radiation pressure equals to the gravitational force, or does not change its size. So the main sequence star is the star which undergo the hydrogen fusion, and its radiation pressure equals to the gravitational force. Explain why it is appropriate for stars such as the Sirius B to be called as a white dwarf star. So why we can say it's a white dwarf? So white dwarf here refers to stars which are usually smaller in size and they have a high temperature. So what are the characteristics of a white dwarf? They have a small size and high temperature. That's why we call them as a white dwarfs. Then two stars in the binary system were formed at roughly at the same time. Explain how we can deduce that the series B was initially much more massive than A. Look, when we have a low mass star, the low mass star, like same as like mass of the sun, these stars have a long duration or a long lifespan in a main sequence. Where a high mass stars usually they have a short time in a main sequence, like they cannot remain in a main sequence for a longer period of a time. So what it shows, they mentioned that the series B is already, it's a white dwarf. When we work out the stellar change, so it's a white dwarf and A is still a main sequence. So this give an idea because massive star cannot remain as a main sequence for a longer time. So series B is already evolved from main sequence to red giant and then to white dwarf. So it means it will have a short main sequence lifespan or a lifetime. So therefore, it has consumed hydrogen fusion quickly. So to consume a hydrogen fusion quickly, it must have a high temperature or it should have a greater density. So we have to relate these. So first, series B or Cyrus B. So Cyrus B, if, according to the question, it is already evolved from main sequence to red giant to the white dwarf. So as the Sirius B evolved from a main sequence to red giant to white dwarf, what it shows? It shows it has shorter main sequence lifetime. If it's having a shorter main sequence lifetime, what it implies, it shows that it undergo hydrogen fusion at a greater rate. And what it implies, if hydrogen fusion happen at a greater rate, it means it has high density and temperature compared to the Cyrus A. And as a result, what will happen? It has more mass or stronger gravity. Like it should have a stronger gravity. So it has more mass.